The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, welcome back. Since we ended abruptly, I want to start with a recap of last time, and then we've got a lot of new ground to cover. So, remember last time we considered the system Q double dot equals U, which is of a general form just a linear feedback system, which in state space form looks like this, where it happens that A and B are particularly simple. And we looked at designing, let's not say designing control, we looked at reshaping the phase space a couple different ways. The first way, which is the sort of 6.302 way, maybe, would be designing sort of by pole placement, by designing feedback gains, possibly by hand, possibly by a root locus analysis. So we looked at manually designing some linear feedback law, U equals negative kx, right? And we did things like plotting the phase portrait, which gave us for Q dot a phase portrait that looked like this. Where this has an eigenvalue of negative 3.75 approximately, and this one had an eigenvalue of negative 0.25. This was all for k equals 1, 4. Okay, and we ended up seeing that just from that quick analysis, we could see phase portraits which looked like this. They'd come across the origin, and then they'd hook in towards the goal, right? And similarly here, this one's so much faster that it would go like this. Okay? And then we looked at an optimal control way of solving the same thing, right? We looked at doing a minimum time optimal control approach. Not specifically so that we could get there faster, even though the minimum time is in the name, because here, remember, we could get there arbitrarily fast by just cranking k as high as we wanted. But actually, for trying to do something a little bit smarter, which is get there in minimum time when I have an extra constraint that U was bounded, in the case we looked at yesterday, was bounded by negative 1, 1. Okay? And in that case, when U was bounded, now the minimum time problem becomes non-trivial. It's not just crank the gains to infinity. And we had to use some better thinking about it. And the result was a phase portrait, which actually, I don't know if you left realizing, it didn't look that different, right? In some ways. Remember, we had these switching surfaces defined here. Okay. And above this, we'd execute one policy, one bang solution, and below it, we'd execute another one. Okay, and the resulting system trajectories, remember this one hooked down across the origin and went into the goal like that. This one really did exactly the same thing, right? They would start over here, they'd hook down here, but this time they'd explicitly hit that switching surface and then ride that into the goal, right? So it's a little bit of a sharper result possibly than the other one, and that final surface was a curve instead of this line, and for that we got to have good performance with bounded torques. Okay. Now we also did the first of two ways that we're going to use to sort of analytically investigate optimality. Anytime, yeah.
Was there a good reason we just explicitly said we want to do linear feedback there? Like we could have done like x1 times x2.
Good, yeah. It's because, well, there's a lot of good reasons. So it's because then the closed loop dynamics are linear, and we can analyze them in every way, and including making these plots in ways that I couldn't have done if this was nonlinear. Another answer would be that this is what 90% of the world would have done, if that's satisfying at all. I think that's you know, the dominant way of sort of thinking about these things. X1 times X2 is comparably much harder to reason about, actually.
I totally agree, but is there like a system that the optimal controller lies in a space that you have to take into account these different like combinations?
Good. So this is an example of a nonlinear controller, right? It happens that the actual control action is either 1 or -1, right? But the decision plane is very nonlinear, right? So that's absolutely a nonlinear controller. Okay, it came out of optimal control on a linear system, but the result is a nonlinear controller. Okay. Now, certain classes of nonlinear controllers are going to pop out and could be easier to think about than the broad class, but you're going to see lots of instances as quickly as we can. Okay, so we actually got that curve by thinking just about, just using our intuition to reason about bang bang control. Okay, at the end I started to show you that the same thing comes out of what I'll call solution technique 1 here. I wouldn't call it that outside of the room. Sorry, that's just me being clear here, right? Which was based on Pontryagin's minimum principle. Okay, which in this case is nothing more than just, let's write it down exactly what we mean by this cost function, right? We have some, let me a little bit more loose. We have J, some cost function we want to optimize, which is a finite time integral of 1 dt. That sounds ridiculous, but we're just optimizing time, right? But we want to optimize that subject to the constraints that x dot equals f of xu, which in this case is our linear system, and the constraint that u was -1 in that regime, and the constraint that at time t, xt had better be at the origin. Given those constraints, we can say let's minimize t. We're going to minimize that j. Sorry, I already got the t in there. So minimize with respect to trajectory in xu, that cost function. I use this overbar to denote the entire time history of a variable like x, t1 to t final or something like this, t0 to t final. Okay, that's how we set up the problem. It's just optimizing some function, but subject to a handful of constraints. Okay, Pontryagin's minimum principle is nothing more than putting Lagrange multipliers to work to turn that constrained optimization into an unconstrained optimization. Okay, and for this problem, we can build our augmented system. I'll call it J prime here, which just is the same thing but taking in the constraints. So first of all, we've got a constraint on xt equaling 0, so I can put that in as a Lagrange multiplier. Let's say lambda times something that better equals 0, which in this case was just xt, and then plus 0 to t 1 plus the constraint on the dynamics, which I'll call it a different Lagrange multiplier, p times f of xu minus x dot, this whole thing dt. Yes?
How do you impose the constraint that u is?
Awesome. Good question. So it turns out what we're going to look at, we want to verify that this thing is optimal. Okay, so you might want to put that constraint right in here, but it's more natural. Let me finish my statement here. The way we're going to verify optimality of this policy is by verifying that we're at a local minimum in J prime, right? I want to say that if I change x, if I change u, if I change p in any admissible way, then J is going to change. Small changes in here is not going to change this. I'm at a local minima in J prime. That's the minimum principle idea, right? I just want if I'm at a minimum of a function, the gradient is 0. In the Lagrange multiplier, the minimum of this augmented function, the gradient had to be 0. So if I change any of these, I want that change to be 0. Okay? So it turns out that the more natural way to look at this bound in U is by not allowing U to change outside of that regime. Okay. This is actually fairly procedural, right? So you end up doing this calculus of variations on J prime. But I made a call earlier today. I think it's going to, if I do it right now in the beginning of class, I'm going to lose you. I'm going to bore you and lose you. But it's in the notes and it's clean. So I'm going to leave that hanging and let you look at it in the notes without typos that I might put up on the board. Okay? Because I want to move on to the dynamic programming view of the world, right? Sort of the other possible solution technique. Okay, so today we're going to do, you can think of it as just solution technique 2 here. And it's based on dynamic programming. Now, the computer scientists in the audience say, I know dynamic programming. It's how I find the shortest path between point A and point B without reusing memory and things like that. And you're exactly right. That's exactly what it is. It happens that the dynamic programming has a slightly bigger footprint in the world. There's a continuous form of dynamic programming. Okay, so the graph search is a very discrete form of dynamic programming. So I'm going to I'm actually going to work from the graph search sort of view of the world, but to make the continuous form that works for these continuous dynamical systems. Okay? And we're going to use this to investigate a different cost function. Which is just this, still subject to the dynamics. Which in this case was the linear dynamics. Okay. So before we worry about solving it, let's take a minute to decide if it's a reasonable cost function. It's different in a couple of ways, right? First of all, there's no hard limit on u, but I do penalize for u being away from 0, right? So it's sort of a penalty on u, not a hard limit, okay? And then these terms are penalizing it from the system from being away from the origin, right? And instead of going for some finite time and minimizing time, I'm going to go for an infinite horizon. So the only way to drive this thing, the only way actually for j to be a finite cost over this infinite integral is if q and q dot get to 0 and you do u of 0 at 0. Okay? Otherwise this thing's going to blow up. It's going to be an infinite integral. Okay, so the solution had better result in us getting to the origin, it turns out. Okay, but I'm not trying to explicitly minimize the time. I'm just penalizing it for being away, and I'm penalizing it for taking action. Okay? Now, what's the name of this type of control? Who knows it? I think yeah, LQR, right? So this is a linear quadratic regulator. Okay, it's a staple of, it's sort of the most used result from optimal control. Everybody opens up MATLAB and calls LQR, but you're going to understand it. Okay, good. But to do LQR, to understand how that derivation works, we're going to go through dynamic programming.
Didn't we use the same cost function there as well?
Awesome. Okay. So why don't I put that cost function down and just do Pontryagin's minimum principle? Okay. There's only one sort of subtle reason, which is that that's an infinite horizon cost. Okay. So I was going to say this to the end, but let's have this discussion now. So this is an infinite horizon. Pontryagins is used to verify the optimality of some finite integral. Okay. So let's compare well. I know you know value duration, the dynamic programming. So maybe let me say what dynamic programming is, and then I'll contrast them. Yeah. Yeah. Okay, but do people sort of? I just want to understand what happened. We've got two different cost functions, two different solution techniques for now, and we're going to address in a few minutes why I did different solution techniques for the different cost functions. But I hope they both seem like sort of reasonable cost functions if I want to get my system to the origin. Okay. Different, we're going to look at what the result is, the different results. And actually something I want to leave you with is that you can you can in fact do lots of different combinations of these things. You could do quadratic costs and try to have some minimum time. There's there's lots and lots of ways to formulate these cost functions. These are two sort of examples, but you can do minimum time LQR, you can do all these things. Okay, but the way we're going to derive the LQR controller is by thinking about dynamic programming. And to do that, let me start with the discrete world, where it makes sense. So let's imagine I have a discrete time system. So x of n plus 1 is f of xn un. And I have some cost function. Now remember, in the Pontryagin minimum principle, we showed that there's a sort of a general form that a lot of these cost functions take. In the discrete form, it's h of x at capital N plus a sum instead of an integral, right, of n equals 0 to n minus 1 g of xn un. Okay. Now, again, I said this sort of additive form of the cost functions is pretty common, and you're going to see right now one of the reasons why. The great thing about having these costs that accumulate additively over the trajectory is that I can make a recursive form of this equation. Okay. So in particular, if so I should call this really what I've been calling J. That's really the J of being at x0 at time 0. And I can compute J of being at x0 at time 0 and incurring the rest of the cost recursively by looking at what it would be like to be at some state x at time n. And that in this case is just h of x of n. And then thinking about what it would be like to be at some j of x at n minus 1, right? And that's going to be g of x n minus 1 u of n minus 1 plus h of xn. Let me be even more careful, and I'm going to say let's evaluate the cost of running a particular policy. Un is just some pi of j of xn.
Sorry, why did the first x has 0 in it, but the rest of x is
Okay, so why did I put x0 here? That was intentional. I'm trying to make x0 the variable that fits in here. Here x is the variable that fits in here, but you're right, I could be a little bit more, I should be more careful. So now j, a function of this variable x at time n should really just be h of x. Yeah, good. So then this is, I could say it this way. The other way I could say it is j at x minus 1 equals x. Maybe that's the best way to rectify it. Okay, and when I'm evaluating the cost of a particular policy, I'm going to use the notation j pi here to say this is the cost I should expect to receive given I'm in some state x. To make it even more satisfying, let's just be the same everywhere. This is x0, and here I'll say x0 equals my x. Okay, if I'm in some state x at time 0, executing policy pi, I'm going to incur this cost, right? If I'm at in some state x at time n, incurring this, taking this policy, I'm going to get this. Here I'm going to get this. And even when I'm executing policy pi, I can even furthermore say that xn is f of xn minus 1, pi of xn minus 1. It's probably impossible to read in that corner. Okay. So you can see where I'm going with it. It's pretty easy to see that j pi of x at some n is just the one-step cost, g of x and un, plus the cost I expect to see given I'm at xn plus 1 at time n plus 1. Okay. So the reason we like these integral costs, or the sum of costs in the discrete time case, is because I can do these recursive computations. And the same thing true if I look at, if I define what the optimal cost is. Okay. So let's now define J star to be the cost I incur if I follow the optimal policy. Which is pi star. Well, it turns out same thing works. But now there's an extra term here. Okay. So it's easy to see that the cost to go of following a particular policy is recursive. It's more surprising that the cost to go of the optimal policy is equally recursive with a simple form like this, min over u. Okay. And this actually follows from something called the principle of optimality. Anybody see the principle of optimality before? Okay. It says that if I want to be optimal over some trajectory, I'd better be optimal over from the end of that trajectory. So if I want to be optimal for the last, from n minus 2 to the end, then I'd better be optimal from n minus 1 to the end. Okay, so it turns out if I act optimally in one step by doing this min over u, and then follow the policy of acting optimally for the rest of time, then that's optimal for the entire function. Okay? Okay. Okay, good. So we got a recursive form of this cost to go function that we exploited with the additive thing, the additive form. And now the optimal policy comes straight out. The best thing to do if you're in state x and a time n is just the argmin over u of gxu plus j star xn plus 1. n plus 1 with that same xn plus 1 defined by. Okay? So in discrete time, optimal control is trivial. If you have an additive cost function, all you have to do is figure out what your cost is at the end, and then go back one step, do the thing that in one step minimizes the cost and gets me to the lowest possible cost in the future. And if I just do that recursively backwards, I come up with the optimal policy that gets me from any x in n steps to the end. Okay? Does that make sense? Ask questions. Do people buy that? Is that obvious, or does that need more explanation? Okay. Ask questions if you have them. All right, so we're gonna use the discrete time form again when we get to the algorithms, but I'm trying to use it today to leapfrog into the continuous time conditions for optimality. Okay. So what happens if we now do the same sort of discrete time thinking, but do it in the limit where the time between steps goes to 0, okay? So let me try to do the limiting argument to get us back to continuous time. Now we've got our cost function again is h of x at capital T plus the integral from 0 to t of gxu dt. The analogous statement from this recursion in the discrete time is that jx at t is going to be a limiting argument as dt goes to 0 of the min over u of g xu dt plus j x of t plus dt t plus dt. Okay. This is now, that's just the limiting argument as dt goes to 0 of the same recursive statement. I'm going to approximate j x of t plus dt as, this is j star, let me not forget my stars, as j star at x and t plus partial j star partial x x dot dt plus partial j star partial t dt, right? It's a Taylor expansion of that term. Okay. If I insert that back in, then I have j star x of t equals the limit as dt goes to 0, min over u g xu dt plus partial j star partial x dot is just f of xu, remember, dt plus partial j partial t dt. Now I left off that j x there because that actually doesn't depend on u, so I'm going to put that outside here, plus j x of t. Those guys cancel. And now I've got a dt everywhere, so I can actually take that out and my limiting argument goes away. And what I'm left with is 0 equals min over u g of xu plus partial j partial x star plus partial j partial t. This is a very famous equation. It'll be used a lot. It's called the Hamilton-Jacobi-Bellman equation. Yes, did I miss?
X dot in the middle term.
Here?
Last equation, yeah, that X dot in the middle.
Oh, thanks. Good. This is f of xu. Good. Thank you. Good. Thank you. That is the Hamilton-Jacobi-Bellman equation, often known as the HJB. So Hamilton and Jacobi are really old guys. Right, Bellman's a newer guy. He was in the 60s or something. A lot of people say Hamilton, Bellman, Jacobi, but that doesn't seem quite right to me. That's some guy in the 60s sticking his name in between Hamilton and Jacobi. So I would probably say HBJ a couple times in the class, but whenever I'm thinking about it, I say HJB. Okay. Okay, so we did a little bit of work in discrete time, but the absolute output of that thinking, the thing you need to remember is this Hamilton-Jacobi-Bellman equation, okay? These turn out to be the conditions of optimality for continuous time. Let's think about what it means. So do you have yet a picture of this sort of what J is? Okay, J is a cost to go. It's a function over the entire landscape. It tells me if I'm in some state, how much cost am I going to incur with my cost function as it runs off into time, right? In the finite horizon case, it's just an integral to the end of time. In the infinite horizon case, it's I'm started this initial condition and I run my cost function forever. Okay, so J is a cost landscape, a cost to go landscape. This statement here says that if I move a little bit in that landscape, in x, okay, scaled by this x dot, then the thing I should incur is my instantaneous cost. Okay. So the way my cost landscape, the difference of being an initial condition 1 versus being an initial condition 2, if they're neighboring, right, goes like the cost function. Okay, and there's the cost function, the cost to go function lives in x and it lives in time. Okay. It's one of the most important equations we'll have. Hamilton-Bellman-Jacobi equation.
So we can take out that the partial k star out of it and get something similar to that equation. Because that one is independent of u, right? The last term. So if we take that out, basically the differences between the value of the two neighboring with respect to time, like in this time and going to the next time, that sort of seems like a TD error.
Oh yeah, good. There's absolutely that. This is exactly the source of the TD error and the Bellman. Yeah, it's exactly the Bellman equation. So yeah, so you're right. Partial J partial T could have been outside the min over U. It doesn't actually have U, but we're going to see all those connections as we get into the algorithms. But for this now is a tool for proving analytically and deriving analytically some optimal controllers. Okay. We need one more. We need to say something stronger about how useful that tool is. So there's the sufficiency theorem is what gives this guy teeth, okay? So I told you that the Pontryagins minimum principle was a necessary condition for optimality. It wasn't necessarily sufficient. If you show that the system satisfies the Pontryagins minimum principle, then you're close, but you actually also have to say it uniquely solves that. It's the only solution to that. It solves the Pontryagins minimum principle. So there's extra work needed. The theorem we're putting up here is going to say that if this equation is satisfied, then that's sufficient to guarantee that the policy is optimal. Okay. So given a policy pi x of t and a cost to go function, j pi x of t, if pi is the argument of this, if pi is the policy which minimizes that, for all x and all t, and that condition is met, then we can, that's sufficient to give that j pi x of t equals j pi of x of t and pi x of t, pi star x of t. Okay? The proof of that I'm not even going to try. It's sort of tedious. It's in Bertzikas, if you like, Bertzikas' book. But we're going to use this a lot. Okay? So if I can find some combination of j, pi, and pi that match that condition, then I've found an optimal policy. Okay. Let's use this to solve the problem we wanted. Okay. The linear quadratic regulator in its general form says I've got a system x dot equals ax plus bu. And let's say I have a cost function, j of x0 is h of x t, the same thing I've been writing all day here, g of xu dt, where x0 equals x, where h in general takes the form x transpose qfx, and g takes the form x transpose qx plus u transpose ru. To make things, to be careful, we're going to assume that we're going to enforce, we're choosing the cost function. We're going to enforce that this is positive definite, making sure we don't get any negative cost here. Okay, and similarly, actually it only has to be semi-definite. Q transpose equals Q greater than or equal to 0. And R transpose equals R. That one does have to be positive definite. Okay, here's a pretty general linear dynamical system, quadratic regulator cost. To satisfy the HBJ, we simply have to have this condition met, right? So 0 equals min over u x transpose qx plus u transpose ru plus partial j partial x star times ax plus bu plus partial j star partial t that had better equal 0. So I need to find that cost to go function which makes this thing 0. Okay. Turns out the solution to these things, we can just guess a form for J. Okay, let's guess that J star x of t is also quadratic. Again, with a positive, it's going to have to be positive. Could be. In that case, partial j partial x is 2x transpose s of t. Partial j partial t is x transpose s dot of t x. Okay. Let's pop this guy in. I don't want to just crank through here. So does it make sense at all that the j of xt would be a quadratic form like that? Why is that a reasonable guess? Yeah?
Well, at the final time, each form will match the penalty.
Perfect. Okay, so in the final time, that's a reasonable guess because it started like this. Yeah, and it turns out, I mean, we're actually gonna see it by verification, but for the linear system, when I pump the cost backwards in time, this quadratic cost, it's gonna have to stay quadratic. Okay. Okay, so I've got 0 equals min over u, x transpose qx plus u transpose ru plus 2x transpose s of t, bless you, times ax plus bu plus x transpose s t x. I need that whole thing to work out to be 0. Okay? For the minimizing u. So let's figure out what the minimizing u is now. Is it okay if I just sort of shorthand, I'll say the gradient of that whole thing in square brackets with respect to u here? Okay. Is going to be, what, 2 ru, or u transpose r, I guess? We're going to try to be careful that this whole thing is a scalar, right? We're always talking about scalar costs. I've got vectors and matrices going around, but the whole thing has to collapse to be a scalar, right? The gradient of a scalar with respect to a vector, I want it to always be a row vector. The gradient of a vector with respect to a vector is going to be a matrix, okay? So try to be careful about making that gradient better be a row vector. Plus what's left here? 2x transpose s, that guy there, right? But I have to take the transpose of that, so it's 2 b transpose s of t. The st transpose is not x. No, I screwed up, sorry. still X transpose. I'm trying to X transpose S of t B. Okay, that thing has to equal 0. And that's where I get my transpose back. So U star, the U that makes this gradient 0, is going to be, those 2's cancel. It's going to be negative R inverse B transpose S transpose X. Okay? Which, it's important to realize that was actually it's equivalent to writing negative half R inverse B transpose partial J partial X transpose. Okay, so what does this mean? So I've got some quadratic approximation of my value function. Okay, it's 0 at the origin, always and forever. If I'm at the origin, I'm going to stay at the origin. My cost to go is 0, right? The exact shape of the quadratic bowl changes over time. The best thing to do is to go down. So negative of partial J partial X is trying to go down the cost to go function, right? I want to go down the cost to go function as fast as I can, right? But I'm going to wait. I'm going to change possibly the exact direction. Rather than going straight down the cost to go function in X, I might orient myself a little bit depending on the weightings I put on the cost I put on the different U's. Okay, so I'm going to rotate that vector a little bit. This is what I can do, and this is what the weighting I've done. Okay? So the best thing to do is to go down your cost to go function, get to the point where my cost to go is going to be as small as possible, filtered by the direction I can actually go, and twisted by the way I've penalized actions. Okay? And it's sort of amazing, I think, that the whole thing works out to be just some linear feedback law, negative kx. Yet another reason Albor is to use that form. Okay. Sorry, I should be a little careful. It depends on time, right? So it's k of t x. Why should it depend on time? This is what's that?
Because we switch.
Because we switch what?
The actuation.
There's no hard switch in the actuation here. This is saying I'm going to smoothly go down a value function. Right? This one isn't the bang bang controller. This turns out to be a smooth descent of some cost to go function. Yeah.
The S of t, the partials hiding
I mean, S of t is time dependent itself.
Yeah, so RB is.
So intuitively, why should I take a different linear control action if I'm at time 1 versus time 2?
Because you're time limited, so if you're very close to the final time, you want to put lots of control because you don't have much time to release.
Awesome. Yep. This is a quirk of having a finite horizon cost function. Okay. In the infinite horizon case, it turns out you're going to just get a u equals negative k of x, where k is a variant of time. But in the time finite horizon problem, there's this quirk, which is the time ends at some point, and I have to deal with it, right? Like the bank closes at 5, right? If I'm here and it's 4:50 and the bank closes at 5, I better get over there faster than if it was 4:30 and the bank closes at 5, right? In my mind, actually, there's a lot of problems that are, bank closing is a weird one, but there are a lot of problems that are naturally formulated as finite horizon problems. things, maybe a pick and place. The minimum time problem was a finite horizon, pick and place. There are a lot of problems which are naturally formulated as infinite horizon. I just want to walk as well as I possibly can for a very long time. I don't need to get to some place at a certain time. Okay. But in many ways, the finite horizon time ones are the weird ones because you always have to worry about the end of time approaching, right? Okay. How do we get ST? Okay. Well, it's the thing that makes this equation 0, right? So what is that thing? So I figured out what the minimizing u is. I can insert that back in. So I get now 0 equals q plus x transpose. I'm going to insert u in. K, or I'll do the whole thing actually. S of t, b, r inverse times r inverse. So I'm going to go ahead and cancel those out. B transpose S of t x, right? And the negative signs, because there's two u's there, the negative sign didn't get me. And then plus 2x transpose S of t ax plus, so minus b r inverse b transpose S of t x plus x transpose S dot of x. Okay. It turns out that this term here should be the same as that term there, modulo a factor of 2. If you look, it's S, B, R inverse B transpose S. Okay, so this one actually, I can just turn that into a minus. Okay. And it turns out that everything has this X transpose matrix X form. Okay. So I can actually, in order for this thing to be true for all X, it must be that the matrix inside had better be 0. So it turns out to be 0 equals Q minus ST B R inverse B transpose ST plus 2 ST A plus S dot of T had better be equal to 0. Okay. Now I made some assumptions to get here. Remember what assumptions I made? The big one is that I guessed that form of the value function. Okay, and one of the things I guessed about it was that it was symmetric. So let's see if we're looking symmetric. So Q we already said was symmetric. That's all good. That guy is nice and symmetric. That's all good. So this is the one we have to worry about. Is that guy symmetric? It's actually not symmetric like that, but I can equivalently write it as STA plus A transpose ST, since S is symmetric. And that guy is symmetric. I said a very strange thing. I just said that the matrices are, this one is not symmetric. I can write the same thing, and it's this. So what I mean to say is that these are equivalent. For all x, okay? Because this has got to equal this. Okay, so good. Okay. So this equation, which I'm going to write more time since it's an equation that has a name associated with someone famous, deserves a box around it, I guess, right? So this is the Riccati equation. I'm going to move the s over to this side. It's a Riccati equation. Okay, and I also have that final condition that you rightly pointed out, where S of capital T had better equal Q of F. So, direct application of the Hamilton-Bellman-Jacobi equation, I was able to derive this this Riccati equation, which gives me a solution for the value function, right? It gives me a final condition on S, and then the governing equation, which integrates the equation backwards from capital T to 0. And once I have S, remember we said that the U was just negative R inverse B transpose S of T X. So I've got everything. Once I have S, I have everything. Okay, so this is one of the absolute fundamental results in optimal control. It turns out that if you want to know the infinite horizon solution to the, if you look at the solution as time goes to infinity, okay? Remember I wrote my cost function initially was, of the problem we're trying to solve is an infinite integral. It turns out that the infinite solution is the steady state solution of this equation, okay? So if you integrate this equation back enough, it's stable, it finds a steady state where S dot is 0. And that solution when S dot equals 0, the S which solves this that whole thing minus Q is the infinite horizon solution. Okay. If you open up MATLAB, okay, and you type LQR A, B, Q, R, then it's going to output two things. It outputs K and it outputs S. Okay? Solving this thing is actually not trivial, right? So how do you solve that for S? Right? The hard one is it's got this S in both places. But this is a Lyapunov equation again. It's so famous, it comes up so pervasively that people have really good tools for solving it, numerical tools for solving it. So MATLAB's got some nice routine in there to to find S. Okay, and when I call LQR with the dynamics and the QR gives me exactly the infinite horizon S and infinite horizon non-time varying K. Right? If you need to do a finite horizon quadratic regulator, then you actually need to integrate these equations yourself. Okay, I hate going that long with just equations and not intuition, so let me connect it back to the brick now. That was the point of doing everything in the brick world here. Okay, so we've got Q double dot equals U. We've got now infinite horizon Jx is infinite horizon gxu dt, where I said gxu was 1/2 q squared plus 1/2 q dot squared plus 1/2 u squared. Okay. So now that's exactly in the LQR form 0, 1, 0, 0. B is 0, 1. Q is the identity matrix. And R is 1. Turns out I can actually solve that one algebraically for S. If you pump all the symbols in, I won't do it because there's a lot of symbols, but in a few lines of algebra, you can figure out what S has to be. Okay? Just because so many terms drop out with those zeros that actually there's 3 equations and 3 unknowns. And it turns out that S has to be square root of 2, 1, 1, square root of 2. Okay. The U, remember, was negative R inverse B transpose SX, which, if I punch those in, gives me 1 square root of 2 times X. Okay? Which gives me closed loop dynamics of x dot equals ax minus b kx is equal to 0, 1, negative 1 square root of 2 times x. Okay. Now I'm going to plot 2 things here. The first thing I'm going to plot is j of x. Okay. J of x is square root of 2, 1 square root of 2. A little thinking about that, you'll see that it comes out to be an ellipsoid that is actually more sort of shaped like this. Okay. If I draw contours of that function, of that x transpose S x, then my cost to go is 0 here, and it's a bowl that comes up in this sort of elliptic bowl, okay? All right, so what is the optimal policy going to look like given that that's my bowl? Right? We said the best thing to do is to go down the steepest descent of the bowl. Okay? I want to go down wherever I am. I want to go down as fast as I can. Okay? But I can't do it exactly. That was actually sort of a, oh, that's okay. I mean, I can't do it exactly because all I'm allowed to do is change. I have one component that I'm not allowed to change, right? I have my Q is going to go forward independent of U directly. So B transpose SX is going to be give me a projection of that gradient onto the thing I can actually control, which way I can point my phase portrait in that given my control. Okay. And then R is going to scale it again. And the resulting closed loop dynamics, let's see if we can figure that out. So if I take the eigenvectors and eigenvalues of that, oh, it turns out I'm not going to make the plot. My eigenvalues were square root of 2 plus or minus I 1 over square root of 2. With V being 1 over square root of 2. So the best thing I could possibly do is to go down that. If I didn't care about, if I didn't worry about penalizing R, I didn't worry about my control actuation would be to go straight down that bowl. Okay, but because I'm scaling things by, I'm filtering things by what I can actually control, and I'm penalizing things by R, the actual response is a complex response, which goes down this bowl, and oscillates its way into the origin. Okay. Okay, good. It was a little painful, but that is a set of tools that we're gonna lean on when we're making all our algorithms. You've now seen a pretty representative sampling of what people can do analytically with optimal control. Okay, when you have a linear dynamical system, and there's a handful of cost functions which you can analyze either by Pontryagin or dynamic programming, the Hamilton-Bellman-Jacobi sufficiency theorem. Those are really the two big tools that are out there. Okay. In cases, especially for linear systems, you can analytically come up with optimal control policies and value functions. Okay. Why did we distinguish between? Why did I use one in one place and the other in the other place? Well, it turns out the Hamilton-Bellman-Jacobi sufficiency theorem has in it these partial j's, partial x, partial j, partial t. Okay, so it's only valid actually if partial j, partial x is smooth. The policy we got from minimum time has this hard nonlinearity in the middle of it. Turns out the value function that you have in the minimum time problem also has a hard nonlinearity in it. Okay, if I'm here versus here, it's smooth, but the gradients are not smooth. The gradient is discontinuous. So on this cusp, partial j, partial x is undefined. Okay, so that's the only reason why I didn't lean on the sufficiency theorem completely. Okay, how did Pontryagin get around that? The sufficiency theorem is talking about it's looking at roughly over the entire state space. It's It's looking at variations in the cost to go function as I move in x and in time. Pontryagin, if you remember, was along a particular trajectory. It was verifying that a particular trajectory was locally optimal, okay? And it turns out in problems like this, in these bang-bang problems, along a particular trajectory, my cost to go is smooth. Okay, the cost to go in the minimum time problem was just time, right? So the time I get, the time it takes for me to go to here is just smoothly decreasing as I get closer, like time. Okay, along any trajectory with these additive costs, the value function is going to be smooth. But along a non-system trajectory, some line like this, partial, if I just look at how j varies over x, it's not smooth. Okay? So Pontryagin is a weaker statement. It's a statement about local stability along a trajectory, but it's valid in slightly larger domains because it doesn't rely on value functions being smoothly differentiable. Okay? Now, for the first order, or for the double integrator, the brick on ice, we could have just chosen our k's by hand and pushed them higher or smaller. We could do root locus. We could figure out a pretty reasonable set of k's of feedback gains to make it stabilize to the goal. LQR gives us a different set of knobs that we could tune. Now we could more explicitly say what our concern is for getting to the goal by the Q matrix versus what our concern is about using a lot of cost in the R matrix. Okay, so maybe that's not very compelling. Maybe we just did a lot of work to just have a slightly different set of knobs to turn when I'm designing my feedback controller. But what you're going to see is that for much more complicated systems that are still linear, or linearizations about very complicated systems, LQR is going to give you an explicit way to design these linear feedback controllers in a way that's optimal. Okay, so we're actually, doing a variation of LQR now to make an airplane land on a perch, right? For instance, we're going to use it to stabilize the double inverted pendulum, the Acrobat, around the top. Okay, so it's going to be a generally more useful tool. Down at the brick double integrator level, you could think it's almost just a different set of ways to do your root locus. Okay, you have now, through two sort of dry lectures relative to the rest of the class, learned two ways to do analytical optimal control. Okay, one is by means of the Pontryagin minimum principle, one's by means of dynamic programming, which through the HJB sufficiency theorem. Okay, and you've seen some representatives of what people can do with those analytical optimal control. And it got us far enough to make a brick go to the origin, okay? Right, and it'll do a few more things, but okay, so that's about as far as we get with analytics, right? We're going to use this in places to start algorithms up, but if we wanted, for instance, solve the minimum time problem or the quadratic regulator problem for the nonlinear dynamics of the pendulum, right? If I take my x dot equals ax plus bu away and give it the MGL sine theta, then most of these tools break down. Okay. Next Tuesday happens to be a holiday, virtual Monday, so we won't do it on next Tuesday. But next Thursday, I'm going to show you algorithms that are based on these. This is the important foundation that are going to solve algorithmically the same optimal control problems that we're, more optimal control problems than we can solve analytically. Okay? And then we'll go on from there to more and more complicated systems.